we're going to learn about t-tests for differences in means. So like I said in the intro, we use t-tests when we want to know if there is a difference in means between two groups in the population, right? Remember that we do the reason for any type of hypothesis tests in statistics is to make sure that what we're observing here in our sample data is not there just a result of sampling error, right? That there is some difference out there in the population too, right? So again, any hypothesis tests that you're going to do in your life in statistics is for that reason. You want to know if what you're observing in the sample is not there just by sampling error, that there is some relationship or some difference in the population as well. All right, so suppose that, as an example, suppose that we took a random sample of students, in CHHS students, and we asked them their gender, and we also asked them about their GPA. And then we analyze this variable GPA, which is, of course, interval level variable. It can take pretty much any value between 0 and 4. And we get the average GPA for male and for female, right? And we get two values, right? The average for female and the average for male. In this case, let's suppose the GPA, the average GPA for male students is, or respondents, is 2.5, and the average GPA for female students is 3.5. Now, there is a difference, right? There is a difference in this sample. Now, we cannot make, we can't really make that an inference about the population. We cannot say just with this sample result that in the population, male students or CHHS male students have lower GPAs than CHHS female students. We would have to do a hypothesis test to rule out the possibility that this is just the result of these differences that we observe in the sample is just there due to sampling error, right? So the t-test would allow us or tell us if the difference we observe in the sample means, right, is also taking place in the population, or if it's probably just the result of sampling error. You may remember the steps in a hypothesis test, and these are very, very similar than the hypothesis, than the chi-square test that we talked about last week, with some small differences, right? The first difference is that there's three types of t-tests. Okay, they're all comparing means, right? They're all comparing two averages, but they differ in terms of what groups you're comparing, okay? And we'll talk about that. This is very simple. The second step is to state the null hypothesis and the alternative hypothesis. The null hypothesis in most hypothesis tests is that there is no relationship, which in this case would be there's no difference, right? If there's no relationship, there's no difference in the means between the two groups. So the null is always that there is no difference. And the alternative hypothesis usually are that there is a difference, right? If it's two-tailed. The third step is, again, to determine the sampling distribution of the t-statistic when the null is true, right? And this we do because we want to compare our difference, right? Our t for our little sample to the t's that come from a population where there is no difference, right? And in this population where there's no difference, we have to know how that is distributed, right? And for that, we need to determine that sampling distribution. That's what we do. And from that sampling distribution, we're going to choose a significance level, right? And a critical value, critical t, This is some value that we're going to say, hey, this value is pretty rare, right? If we're sampling from a population where there is no difference, right? We're going to choose this pretty rare value, and like that we would get less than 5% of the time. And then we're going to compare it to our own value that we calculate in step 5. And we're going to compare this critical value, which is a pretty rare value that we get when the null is true. And when we compare that, if our value is higher than that rare value, then our value is super rare, right? There's very little chance that our t came from a population where there's no relationship, right? When compared to this critical t. But if this t that we got from our sample is lower than that rare value, that means that the t that we got is pretty common when you're sampling from a population where there is no relationship. So we cannot reject that null, right? And based, if our t is very rare, we reject the null, and we conclude that the variables the means are different in the population, or that they are related. If our t is not very rare, right, compared to the t's in the population where there's no relationship, then we cannot reject the null. And all we can do is say, hey, there's no evidence to say that, that they are related. We have no evidence to conclude that they are related or not, right? We cannot conclude that they're not related. We don't know that. We just have no evidence to say anything really, if we can't reject, right? So let's go over each of these steps. The first one is to determine which test to use. And the first question we have, so there's three types of tests. If you look at these orange boxes, right? The type 1 t-test is when you have two averages, and these averages are for the same individuals or matched samples, right? If the sample for one group is matched, you can match each observation of the two samples. The most obvious example for this is the pre and post test, right? Let's say I tested you in the beginning of the course of your knowledge of statistics, right? And you have your grade. And then I tested you at the end of the course on your knowledge of the statistics. Then I know it's you. I can compare your individual grade to in the pre to your individual grade in the post. They are matched by your name, right? And I can do that for every observation. Those are matched samples. And if you have those kinds of matched samples, you are using a type 1 t-test. It's called a paired sample t-test, okay? That is very, very rare in survey. In survey analysis, it's very rare that you would be able to match respondents from one survey to the other, right? Because most of the time we want our surveys to be anonymous, so we don't ask for the name. It's hard to do that. But in some complex surveys where we're surveying the same people at different points of time and we can match them, then we can do that. And if we want to compare responses for, in one time to respondents in the other, then we would use a paired sample or a matched, right? If, on the other hand, the two groups are not matched, they are not the same, right? They're not the same person, then the samples are not matched, right? Like in this case, when we're comparing female and male students' GPA, right? The GPA for male students is not matched to that of the male students, so they are independent, right? Each of the groups are independent, so they're not matched. If you are dealing with a non-matched sample, then there is, you know, a small little detail there. You have to ask yourself, hey, is the variance for each group different in the population for this variable? Like, is the variance or the standard deviation for GPA for male students, is that different than the standard deviation for the GPA for female students? And if you think there are, then you have to use a t-test with equal variances, right? So that's this is the type 2 test. And if they are, if you think they are not equal, right? You think there's probably more variation in male GPA than in the female GPA, then you would use unequal variance samples. Now, in the old days, this used to be a big issue because there's a little bit of difference in calculation, as we will see later. But in these days, where we have Google Sheets, Excel, all this software, it's just the press of a button, right? Which type of test we choose. So we can do a type 2 and a type 3 and then compare the results if they vary a lot. Usually they don't. But anyway, these are the 3 types. We have to decide, the big decision is, are the 2 groups linked in some way? Are they matched or are they independent? Right? That's the big question. And if they're independent, then you can do equal variances or unequal variances to see. All right. And again, well, we'll see this again when we talk, when we get to the example. All right, and I explained this. It is important to note that in a pair sample, each observation in one sample must be able to be paired with the other one in the other sample, right? If you cannot pair them, then your samples are not matched. That's good. Okay. The second step is to formulate your null hypothesis, right? The null hypothesis in a t-test is always that the mean for group 1 and the group 2 are equal in the population. There's no difference between the means of group 1 and group 2 in the population. And the alternative hypothesis, we can have many, but the best one for me is the two-tail. And this one is that the means for group 1 and group 2 are different in the population, right? The null is that there's no difference, and the alternative is that there is a difference in the population. This is key. Now, you may remember, and this is a little confusing sometimes, that there are other types of alternative hypotheses. They are directional. You can say that the mean for group 1 is larger than the one for group 2, or the mean for group 1 is smaller than the mean of group 2 in the population. These are directional hypotheses. You cannot just choose them like that. You need some theoretical justification for making a claim that one should be bigger than the other one. And so it's better to be more conservative in these things and use a two-tail test, in which your alternative is that your alternative hypothesis is always that the means are different. We don't know if one's going to be higher than the other one. They're just different, right? That's the more conservative alternative hypothesis. Okay, the third step is to determine the sampling distribution of the t-statistic when the null hypothesis is true. That is, when we are sampling from a population where the means are, there's no difference in the means, what do they look like, right? What would this and calculate t-statistics for these 2 samples, and we plot them, what would that plot look like? And just like in the chi-square distribution, There's many chi-square distributions. Their shape is different depending on the degrees of freedom that the distribution has. Same thing happens with the t distribution. The t distribution changes in shape. It starts super flat for small degrees of freedom, and it becomes sort of like a very normal distribution as the degrees of freedom increase. Right now, there's three types of t-tests, and the degrees of freedom are calculated differently for each type of test. When you have a t-test or paired samples, the degrees of freedom are calculated by this first formula, where we have the number of observations, right, that are paired, minus 1. Right? There's I don't know, if there's 50 pairs of observations, then n will be 50, right? But if it's a non-paired, and you think it's a t-test for non-paired samples with equal variances, then the degrees of freedom is given by the number of observations in one group plus the number of observations in the other group minus 2. And if you think the observation or the groups are not paired and they have unequal variances, then the degrees of freedom is determined by the number of observations in the smaller group minus 1. Okay, so you determine which type of test you're going to use, and then you formulate your null hypothesis, an alternative, and then you calculate the degrees of freedom for the type of test that you chose, right? And these formulas are pretty simple, right? Then, just like in the chi-square test, you will choose a significance level for your test, right? And in statistical books, the significance level is usually referred to as alpha. And in social science, and this is basically coming from APA, from the American Psychological Association, we use 5%. So the alpha of 5%, that means that we would, our significance level is 5%, right? And we would choose a t-value from that distribution that we determined, given the degrees of freedom, and we would choose a value that we would get 5% of the time, right, or less. So this significance level, this alpha, it means that we're giving ourselves at most a 5% chance of incorrectly rejecting the null. Okay, all right. Then, and this is pretty much what we're doing, right? This is what a t-distribution looks like, and we say, hey, we're going to look at 5% in this tails, right? And this is a table for two tails because our alternative is a two-tailed one. And we say, hey, if for 9 degrees of freedom, right? For 9 degrees of freedom and 5%, this would be the critical value, this 2.262, right? This critical value is the intersection between those two in a statistics table, but we're going to determine ours using Excel. Excel has a table, can do this in the background. All right. The next step is to calculate your t-statistic for your test. And this is the complicated part of a t-test. The rest is pretty simple. And just calculating the t-statistic for your test depends on the type of test that you're doing, right? In this case, this D means it's the difference between the group 1 and group 2, right? Or the average difference, divided by the standard deviation of the difference, divided by the square root of n. That will be simple. When you have two non-paired samples with equal variances, then it gets a little more complicated. As you see here, you would do this. And if you are assuming unequal variances, you would do this. Now, we are not going to do this because we are in the 21st century and we have Excel to do that for us, right? So, but this is what Excel would be doing in the background to calculate your, your t statistic for your sample. Then you would compare your test statistic, the one you got from that formula, with the one in the critical value that you got, right? That you determined, right, from your table. You would compute your p-value as well, and you would make your conclusion, right? If your critical value tells you that you have less than alpha, like less than 5% chance of getting a t-value higher than that critical value if the null is true, right? So you're comparing your t to that critical value, and you know that critical value, you get that critical value or higher 5% of the time, right? And if you compare your t, if it's higher than that, if that's larger than that critical value, then you reject your null hypothesis and accept the alternative, right? You would say, hey, my sample did not come from a population where there is no relationship. So I accept the alternative and I conclude that my sample came from a population where there is a relationship, where the means are different. But if your t-statistic for your sample is equal or smaller than the critical value, you cannot reject the null hypothesis. And you cannot accept it either, and you cannot accept the alternative, right? So you just say, there is no evidence to say anything here. And you can compute the p-value. Actually, Excel will give you a p-value first. And this p-value is the probability that you would get a t-statistic as high as the one you did if the null was true. So if your p-value is smaller than alpha, right, lower than 0.05, then you reject the null because it's pretty rare that you would get a t like the one you did if the null was true. If the p-value is equal or larger than 0.05, you cannot reject the null. And then you would write your results, right? And you would say something like an independent samples t-test, that means it's not matched, assuming unequal variances, was used to assess the differences in average GPA between male and female respondents. And then you say, hey, this is what we found. The mean for female respondents was 2.32, and for male students, and yeah, something like that, right? Yeah, there was the difference. Anyway, you will write it like this and say the difference was significant at this alpha level, right? The t was 73, and this was the 70 degrees of freedom. 5.2 was the value. That's less than 0.01%. That's my p-value. It was smaller than 1%. And write the results like that, right? If you could not reject your null, you need to say it, right? You can say this difference that we saw in the sample was not statistically significant at this level. Okay. Okay. So that is all the theory of the t-test. Let's go and look at how we would do this in real life with a real data set and in Google Sheets.